Hey, this is my Physics Lab 3 recording, and for the introduction to this lab, the purpose of a lab is that for part 1 of the lab, we were trying to find the mass of the black hole using our knowledge of Newton's second law and how the parallel and perpendicular forces affect the motion of an orbiting object. And in part 2 of the lab, we used the mass of the black hole we found in part 1 of the lab to compute the trajectory and initial launch velocity of a spaceship that needs to get close to a black hole, but not so close that it will get sucked into the black hole. The fundamental principles that we used during this lab are the Newton's second law, or the momentum principle, in which we use these principles to observe the net interactions between the system and its surroundings. And the formulas we use in this experiment are Newton's second law: F net is equal to dp over dt. F net is equal to it's the components of the force, and we also have dp over dt is equal to dp dt parallel plus dp dt perpendicular. We also use the velocity update formula, which is vf is equal to vi plus f net over m times delta t. The position update formula, rf, is equal to ri plus v average times delta t. And the universal gravitational formula, which is fg, is equal to negative g times mm over r squared. And we use these principles to calculate the unknown mass of the black hole, as well as the velocity required for the spaceship to get as close to the black hole as possible without getting pulled in. For the preview of results, in part one of the experiment, we utilized the gravitational force formula, net force formula, and the momentum principle in order to solve for the F net and its components and the mass of the black hole. For the F net, I got 7.61 times e to the 28th power, and for F net parallel, I got 1.218 times e to the 28th power, and F net perpendicular, I got 7.525 times e to the 28th power, and for the mass of the black hole, I got 9.1575 times e to the 33rd power. For the results of part 2, in part 2 of the experiment, we needed to find the net force acting on the planet as well as the net force acting upon the spaceship for each time step in order to figure out how the velocity the spaceship needed in order to fly as close to the black hole while not getting pulled in. For the initial velocity in the x direction, I got negative 3.53 times e to the 7th power meters per second, and the initial velocity in the y direction, I got 1.4 times e to the 6th power meters per second. For part 1's initial conditions, the gravitational constant, g equals 6.7 e to the negative 11th power, the mass of the star, 2 times e to the 30th power, the time interval between important data points is delta t is equal to 86,400 seconds, and the time for the first observation data point is t equals 0, with the surroundings being the black hole and the system being the planet. For the actual coding, we calculate the initial and final momentum vectors right here using just the regular momentum principle m times v, and we calculate the change of velocity and the change of momentum here by using just a general equation for the change of momentum and change of velocity, which is just the final minus initial, and we calculate dp dt, which is just delta p over delta t, and using Newton's second law, we're able to deduce that F net is equal to dp dt. And calculating dp dt parallel, we calculate right here, and using Newton's second law to calculate F net parallel, we introduce that F net parallel is equal to dp dt parallel, and the same thing goes for calculating dp dt perpendicular, which is F net minus F net parallel, and using Newton's second law, we can calculate that F net perpendicular is equal to dp dt perpendicular. And to calculate the mass of the black hole, we find the radius, we find the mass of the black hole is equal to the magnitude of F net times the radius squared over g times the mass of the star. And then right here, we're just finding the average of the mass of the black hole. And for the results I got and the possible sources of error, some possible sources of error are some sources of error may have occurred here are the mass of the black hole being a bit off since it's approximation and not the true value of the mass of the black hole, since we took an average to find the mass of the black hole. And then, as you can see here, the F net is equal to this value, F net parallel equal to this value, F net perpendicular equal to this value, and the mass of the black hole. For part 2's initial conditions, the mass of the black hole is equal to what we got in the part 1. Gravitational constant is the same as before. Mass of the planet is 9 times e to the 20th power. Mass of the spaceship is 7 times e to the 10th power. Delta t is 1 second. Initial time is 0 seconds, with the surroundings being the planet, black hole, and the system being the spaceship. For the actual code, we're just finding the gravitational force of the black hole on the planet, the ship on the planet, and then the net force together, which is just adding those two forces before. And then we find the gravitational force of the black hole on the ship, and then the gravitational force of the planet on the ship. And then finding the F net of the forces on the ship, which is just adding those two forces mentioned earlier together. All these gravitational forces can be found using the opposite of g times m over r squared that we deduced or denoted in the beginning of the slides. And then let's wait for that. Then for the results and possible sources of error, I got my initial velocity of the spaceship in the x direction to be negative 3.53 times e to the 10 or e to the 7th meters per second, and the initial velocity of the spaceship in the y direction to be 1.4 times e to the 6 meters per second. Here's the produced picture that it gave me, which, as you can see here, it's pretty close to the black hole. And some sources of error that may have happened are the inputs for the initial velocities of the spaceships have been more accurate since I used and everyone else used trial and error to find the velocities. And for the additional questions, what does it mean? Although the Fnet and dPdt are technically equal to each other, the way of getting them are different. And in this experiment, we were able to directly calculate the value of dPdt, while we could only deduce the value of Fnet because they are technically equivalent values. And for the what if, using the initial velocity for the ship of negative 3.53 times e to the fifth meters per second for the initial velocity in the x direction, and 9 times e to the sixth power meters per second for the initial velocity in the y direction, I was able to achieve the orbit around the black hole, as you can see here. And that's it.